Okay, hello everyone. Welcome to our monthly PostSync webinar. Today, I'm going to be covering the Nanosurf Drive AFM. I thought it would come in handy to do a live demonstration to serve as an instructional video and hopefully get some more people interested in the AFM as well and what it can do. So we're going to cover imaging today as well as some indentation curve analysis as well for some mechanical tests. All right, so I thought I would start pretty much from scratch. So all I've done is open up the Nanosurf Studio software and I've clicked on measurement here. Also, typically this software looks more like this. So you've got a nice big screen. You can see all of your channels and tools that you need for your imaging, but it's not going to work so well for a Zoom presentation. So I've just scaled it down to a low resolution. So it's going to require a bit more shifting around in the software, but it should be easier to read for everybody. All right, let's get started. So the first thing we're going to do is head over to our camera view here. This is the top-down view. We're looking at the cantilever from the top, and the probe is pointing away from the eyes here towards the sample. First thing we'll do is focus on the cantilever. All right. I'm just going to turn off the auto gain and exposure, turn down the illumination, and crank up the exposure time. And this will help us see the laser. It's not necessary, but it'll just be a better demonstration of what the software is going to do. So for anyone who is using the CX software and is used to manually aligning the laser, I think you'll like this feature. All I've got to do is make sure the correct probe is chosen, which it is. I've got the TAP 190 ALG in there. The correct environment is chosen. I'm going to click Start Auto Setup, and it's going to align the laser for us. Now, as long as the correct cantilever is chosen, it shouldn't take too long. As part of this startup procedure, it's not only going to find the correct laser position, so it's done the readout laser. It positions it up to the side, doesn't need to be in the center. So up to the side is just fine. Next thing it's going to do is optimize the position of the drive laser. So for anyone not familiar, the Nanosurf Drive AFM actually oscillates the cantilever by a secondary laser using like a thermal actuation of the cantilever. Instead of the piezo driving the cantilever, here we have a laser providing some heat power to the cantilever to drive the oscillation, which is supposed to lead to cleaner resonant frequencies, particularly in liquid. So the next step that does automatically for you, which is great, is a thermal tune. So we're looking at the thermal noise of the cantilever in air and fitting some models to it so we can determine the spring constant and the deflection sensitivity of the cantilever. So anyone who's maybe used the AFM a little bit might notice that for the oscillation amplitude of the cantilever, we typically talk in millivolts because we don't always need to know the actual nanometers, the amount that the cantilever is oscillating. But here we get that measurement all in one quick automatic tuning process where now we know, so our sensor reading the laser deflection of the cantilever is giving us a number in volts. And now we know how many nanometers that deflection in volts correlates to. The other thing we know is how much force in newtons a deflection of some nanometers relates to as well. So that's going to enable the mechanical analysis of the indentation curves we'll do towards the end of this session. All right, so we've got a nice little status bar down here. I always like to move this up to the top. So I'm going to do that. Let's get it out the way a little bit. All right. I'm just going to turn the illumination back up and turn the autos back on. Looking at the sample a little bit better. We don't need to actually see the laser anymore. Okay. Now we're back over to this viewport here. And I'm going to just right click on the cantilever and say the tip is here. Because the way the cantilevers are built, the tip doesn't come right out from the edge. It's sort of like a pyramid coming back down towards the center of it. It doesn't really matter exactly where it is, but it'll help us for imaging and getting situated a little bit. All right. So the other thing that we'll do from now, we've got our cantilever set up. So we're going to choose our mode selection. I'm going to take an image first in dynamic force or tapping mode. So chosen our mode. Now we can head to the imaging tab. And the first thing we want to do, so actually these settings up here are layouts for all the features on the screen. So when I first started here, I moved this thermal tune a little bit higher. For example, just move this window so that I could see it and show it more easily. But now that I'm in imaging mode, I don't really need to do the thermal tune again. So I'm going to click this layout 1 here, and it's going to put this frequency sweep in a more, oops, there it is, frequency sweep in a more findable position. So you could even create your own and save them and create your own. Like I've got an Adrian on here and I can click load and that'll load some layout that is useful for me. But I think most people will just find the standard settings pretty useful. Okay, so now we define the resonant frequency of our cantilever, and we are aiming for a free vibration amplitude of around 500 millivolts. So we're going to need to adjust the excitation amplitude until we get the free vibration amplitude we're after. So I'm going to run a frequency sweep. And because we chose the TAP.90 ALG in the first place, it knows roughly the ballpark of where the resonant frequency should be. So it runs the scan in a smaller window, and we found our resonant peak here at, what is that, 165 kilohertz. So I want a larger free vibration amplitude, so I'm going to crank this up. Usually for these tips, it ends up being about 1100 millivolts on the frequency sweep. There we go, 498, pretty close to 500, and that'll do. You also need to make sure you apply. And watch this Z controller in. This Z controller in here is the what they call the amplitude of the cantilever. So once I hit apply, it'll apply that result, and our free air amplitude of oscillation of the cantilever should jump up to that 498. Well, right now it's 495. All right, so one more button to click before we move on. This XY closed loop. It's really easy to forget to click this. I do it all the time. So make sure we turn it on now. You always want to do this far away from the surface too, at least like 100 microns, because it does a big, large XY sweep. So if you're in contact with the sample, you will damage your tip. So make sure to turn this on. So the XY closed loop, we're using a piezo to drive the cantilever in the X and Y axis. And piezos, you tell them where to go, but they don't always sort of go where you tell them to. There's some hysteresis and some lag and things like that with piezos. So what this has is an extra sensor that measures where the piezo is after some voltage is sent to the piezo, and that's a control loop that provides a more accurate XY position. And without it on, you'll notice when you start imaging that your trace and retrace are kind of offset a little bit in the X and Y. They're not matching up very well. So it should be obvious when you start if you haven't turned this on. All right, so I have a little piece of, I'm not sure if it's LDP or HDP, high density polyethylene or low density polyethylene or some sort of branched polyethylene. It is some sort of polyethylene. It's like a soft plastic bag type material. And I just thought it would be an interesting sample for some imaging and mechanical analysis. So right now, I'm about 3 or 4 millimeters away from the sample. So I'm going to find my motor control settings. I'll crank up the speed to about 250 micrometers per second. It's really important you keep this motor step size really small. If this was cranked up to a millimeter and I hit one of these buttons, the surefire way to ruin your morning and break your cantilever with one click. There really is nothing in the AFM that knows how close you are to your sample, so it's very easy to crash into it. All right, so now if I click this once, it'll go 25 micrometers. If I hold down, it'll travel at 250 micrometers per second. So I'm just going to move the mouse closer to the AFM and just watch it by eye and get as close as I feel comfortable, within a millimeter or so, by holding that down. So I can see the AFM tip approaching the sample. And I'm a little under a millimeter away, and that's as close as I want to get. So that'll just make approach a little faster, so not waiting for it to travel a really long way. All right, let's double check. So we've got our Z controller in, or our free air amplitude at a nice 500 millivolts, somewhere around 495 here. I'm going to set the set point. So you can choose your set point in different kind of units. We can do nanometers. You could do force as well, although the actual nanoforce in tapping mode is debated a lot. I'm not really super certain, but so we probably don't want to pick a force. But what we're going to do here is choose a percentage. That's usually the easiest way to run it. And I'm going to run at about 65%. And I'm going to, let's see what I want to show. I think I'll leave it here. So let's click approach. All right, so what's happening now is the Z motor's slowly moving the tip towards the sample. And we have this free air amplitude here. This is our free amplitude in air, but as we start to interact with the sample, that amplitude is going to reduce. And ideally, the cantilever is actually going to be interacting with the surface, touching it. And that physical touch is what's going to reduce this amplitude here. You can imagine all sorts of different modes, like non-contact mode, where we're just interacting with some surface forces, like some van der Waals interactions or some electrostatic forces. But here, I just want to actually physically interact with the sample, have my tip tap the surface. And so this is our free air amplitude. And our set point in our case is 65%. So once the cantilever gets close enough to the surface that the amplitude is reduced by 35% of its original value, so it's down to 65% of its original value. So we're at 500 millivolts in air. We want to keep going down until we get down to 325 millivolts. And then if we check our thermal tune, we have a deflection sensitivity of 171.78. So if we go to a little calculator here and I enter the deflection sensitivity, 171.78, and I might as well add in our spin constant right now, 29.21. Then we can see, let's see, what are we working at here? Oops, let me go down low enough. All right. Just try to put something in, 500. And the calculator. Oh, okay, right. Let's see. 4 times that, so what, like 100 here. Okay. So the 500 millivolts is, what's that? At 90% of that, so about 90 nanometers. And then we're going to 65% of that, so the free air vibration amplitude would be about 65% of 90, so like 58 nanometers, something like that. All right, the approach is done. Let's just do it again so we can take a better look at what this approach looks like. So I'm going to step away from the surface by 25 microns. And then I'm going to approach again. Let's watch the free air amplitude here. You see, as we get close, the free amplitude starts to dip slowly. That's as we're interacting with some of those long-range surface forces. But we should see, ideally, I want to work in where I'm physically touching the sample. So we should see a really sharp drop in the free air amplitude like this here. If you find it's just a sort of a muddy, slow drop in the deflection until you get to the sample, there might be maybe some surface liquid or something like that that's making your cantilever a bit sticky, or some really strong electrostatic forces that are really long distance. And it can end up in a really muddy kind of image. So ideally, you see a nice sharp contact like that. Okay, let's set some settings. I'm going to start off a little slow at 1 hertz. I'm going to stick to 10 microns, get a bit of a feel for where I am. I'm going to close the hood of the AFM. You can't see it on the zoom, but you can see my arm, but not the hood. So I'm closing the hood of the AFM to eliminate any sort of background noise. And you can see that the cantilever has come down close to the sample, and our sample's come into focus. So it's just a thin sheet of polymer that I've cut off of some bag in the lab. All right, I'll hit start on imaging. And you should see the cantilever scan backwards and forwards. All right. So if I click on this video here and use the scroll wheel to scroll in, you can see what we're working with. So this little area here represents the 10 micron area we're imaging in. You can see that image is starting to form here. This dashed line represents I think it's 100 by 100 micron area that we have available to us without opening up the hood and moving the sample. All right, let's start checking out the image quality. So I'm going to start by looking at the topography. I feel like let's see, the blue line is a forward scan. The white line is the back scan. So the way the AFM works is we're going to scan one line forward, the same line backwards, go to the next line. And here we've set it to do 500 points along this line and then 500 lines in that direction. So 500 by 500 pixel image. I feel like we could probably tighten this up a little bit. So I'm going to increase the gain. I'm just going to start times 2 in there. See how it goes. So the gain is a control loop, right? We have our set point of 325 millivolts or 65% of the free air amplitude. And as it scans across the surface, that free air amplitude is changing if it bumps into something. So if the free amplitude drops, the cantilever knows it needs to move up to keep the same tapping force across the surface. So that's a control loop. What's the free air amplitude? Is it 325? Is it more than 325? Move the cantilever down. Is it less than 325? Move the cantilever up. So that control loop, and the rate of that control loop is kind of set by the gains. So the faster that control loop, the better we might track the sample. But if it gets too high, we'll see a bunch of noise. So let's keep just increasing it. I know usually around 64,000 is pretty good for these cantilevers, but I'm going to increase it beyond that until we see a noisy signal. The noise typically shows up most obviously in the Z controller in image. This is actually like an amplitude image or a derived image of this. It's basically, is the cantilever moving up or down? So like rate of change of the cantilever, Z position. Let's crank it up to some value. It would definitely be noisy. Nope, still hanging in there. Okay. 200,000, let's try that. There we go. There's your noise. So that's really obvious. Sometimes it's a bit less obvious, but you can see how noisy this is. Take it back down to 80,000, I think was looking pretty good. Okay, and the noise goes away. Depending on the scale of your topographical image, it's a bit hard to tell the noise. But the Z controller in or amplitude or error image is usually a bit clearer. All right. So I don't want to wait for a 1 hertz image. I'm going to crank it up to 2 hertz. And this is not too important, the quality of this image either. So I might, that's 2.5 again. All right. So typically you'll do a bit of work, get all your settings right. And then what you want to do is hit stop and start again. Because here you can see we've been changing some settings to the image and causing all these sort of defects and differences. So we want to run the entire image at one setting. So that's what hitting stop and start again will do. So I might just pause now so I can edit out this wait later on. Oh wait, I forgot one other thing. So we need to add in the phase signal. And I'll talk about what that phase signal is in a second. Click phase and add it in. Okay. Hit start, let it run. And let's change this to look at the phase signal. It might be a little noisy. I might just drop this gain down and start it again. Let's change the setting. Okay. So the phase signal, the gray line here is the oscillation set, in this case, by that drive laser for making the cantilever oscillate. And in this case, the blue is the shift in phase of that oscillation on, say, this is material A and this is material B. So some sort of composite. So I'm not sure. Maybe this is epoxy and this is bone here or some sort of metal. So the phase shift is actually indicative of material properties. So it's not quantitative at all. You can't say a positive phase shift is more adhesive or more higher stiffness or anything like that. But if you know your sample, you've got some other hints about your sample, you can identify visually different regions or different materials in your sample based on this phase contrast here. And it's typically affected by things like stiffness or adhesion. So let's head back to our image and see if we can see anything interesting. It is possible that for HDPE, we can see some large macromolecular features. It's a bit hard to tell at this zoom level. So we'll zoom in again before picking some spots to do some mechanical analysis on. Some of these darker phase spots might be interesting to look at. Okay, the image is finished. So you can see some interesting features that might be worth investigating here, like this particular dark spot in the phase image here. It's not corresponding to much of a topography change. So often phase can be influenced by like a large topography change. So I don't want to be fooled by anything like that. But I think this is quite a small little bump here, but it has a pretty strong phase signal here. Let's zoom in on that and then after that run some force curves. So to zoom in, this is our back to our cantilever view. I click on this, just use the scroll wheel to zoom in. And I can also, so here I've got the topography, but I could also change this to the phase signal. I think I'll leave it the phase signal. And then I'm going to right click, add imaging frame. I'm going to set it to 4 microns. That's a little smaller. Let's do 3. I'm going to click shift and drag the box to center it over that phase signal there. Make sure that all my settings are still accurate. Like it's 2.5 hertz line rate. Often that gets reset to a default of 5 hertz, which is way too fast. Okay, that's good. And I'm going to hit run on this image position 4. And hopefully we get a better look at that phase change area. And we'll see some more interesting things too as we zoom in. So it's looking pretty good. Our trace and retrace are matching quite well, even with the phase image. So it's looking like a really nice high quality image. It is always striking how quickly you can achieve this kind of resolution if everything goes according to plan with AFM. Okay, the image is finished, and lots of interesting features, that I'm sure we could get into. It looks like maybe there's some macromolecular alignment in this tool. Maybe this is the direction the polymer was stretched or extruded when it was being manufactured. But then this feature here is showing some sort of difference. It's not a lot of topography difference here. So, we can see big topography changes like coming down this slope, over this cliff here, then just some small phase signals probably due to that topography. But here, I think this is a separate phase signal likely indicating some sort of mechanical property difference. Another thing you can do is sometimes it's best to sort of fit some sort of plane underneath the image, and depending on how well you know your sample, these are more or less appropriate, but it's a topic for another time. Okay, so we have our images. Oh, I did forget to write an appropriate file name for these. So down the bottom left over here, what I should have done is type in something like, HDPE, maybe a date, hit enter, and then it would have saved that file in this gallery folder under that file name. But now we'll just have measure 1 and measure 2, so we can work with that. Okay, let's go into spectroscopy mode. So I've got to turn off that oscillation. We want to just go to static force mode. Come back to imaging. Now we'll go straight to spectroscopy. And we'll zoom in. Okay, I'm going to add a spectroscopy grid. And it starts off with 64 by 64. We don't have time for that right now. So I'm going to do something a little smaller. Let's say 4 by 4. And I'm going to do my, let's see, I want to do that. Just make 1. A little smaller. Try. Oops. It changes units on you, so be wary of that. There we go. All right. So this is going to do 4 first force curves. I think it's at the center of, imagine 4 squares making up this square here. At the center of each of those squares, we'll do a force curve. So I'm going to run this one here. So I'm going to actually call this, I'll get rid of that date so the file doesn't get too long, and I'll call this bright phase. And I'm going to hit number 2 for the spectroscopy layout. That'll move a few things around. It's not obvious at first, but we'll head over to them. All right, so actually I want my set point in newtons. And having done this previously, about 100 nanonewtons, a good amount of force. And that'll depend on your tip area and things like that. Okay, so here is our spectroscopy table over here. We are going to so I want 100 nanonewtons, and I can't work out how to get this spectroscopy to show newtons instead of millivolts here, so that's why I have this calculator. So I want at my deflection sensitivity of 171.78, and we got that from the thermal tune here. So we have our deflection sensitivity and spring constant. So I want to know what millivolts to use to get 100 nanonewtons. So if I go up here to 100 nanonewtons, it's roughly 20 millivolts. Okay. So the set point at 20 millivolts, and all the other defaults are fine. Maybe I'll go a little bit slower. Slow it down to say 2 micrometers per second. Okay. See, that's the best way to, I'm going to put this over here so I can monitor it while it's running. Okay. So I want to run this grid position 1. It should move around and do 4 force curves. You can see it approaching. Here's the force curve here. 1, 2, 3, 4. Okay. Oh, it's a 4x4, so it's doing 16, of course. But it's pretty fast, so we'll let it run. You can see it's populating here. It's actually calculating the adhesion from the force curves and plotting that difference there. So it should be showing us the force curve on that. So here's the data viewer. This is the adhesion data. Snap in, max force. See if it's showing it. Yeah. So it's not showing it here. Sometimes it does. Sometimes it's got to work with Nanosurf to get that to work. But if we go over here, check on analysis, gallery here, we can click on this. Layout 2. No, don't need this. Oops, don't need that. There we go. So here's our force curve. There we go. All right, so now for each of these, we can see the individual force curves. There's an approach and then a withdrawal. And the adhesion is pretty much the difference in value between these two numbers here. And that's what it's automatically plotted for us. In the future, there'll be some more analysis available within Nanosurf Studio. But for right now, this is what it's limited to. So I'll show you some other analyzation options in a second. All right, there's our raw data. That's from our bright phase area. So let's take this here, move it over to our dark phase area. Rename this to a dark and hit run. Okay. Now we can just check it under analysis. If I click on dark here, then we should have another set of 16 force curves. And they look pretty good. Okay. So because I'd like to analyze some of these force curves for mechanical properties like Young's modulus, so I'm going to export them to a value that we can use in some different software. So what I'm going to do is export these, a few of them I might do like 4 from the bright and 4 from the dark area to a CSV, and then we can use them in Atomic J. Okay, so I'll fast forward this part of the video just after exporting the data to CSV. Okay, so it's 1. Now we have our raw CSV data, but it's not in a format that Atomic J can digest automatically. You can see it's got separate columns for the advanced, weight, and attract. So I'm going to quickly run a Python script, which will. So I saved everything as this Atomic J conversion, and that's what the script is set to automatically work on. So if I run this, we should now, hopefully, we should now have this converted into columns that we need. the deflection of the cantilever, and also the Z position of the cantilever. So this is how much it's bent, and this is where it is relative to the sample. Okay, so now we can open up Atomic J. Okay, so this is Atomic J, where we can import our raw data and analyze it for certain mechanical properties and adhesion and different things that we can analyze from the force curves. So let's go to File, Open, Add, choose our processed files. Let's choose all of them. Open. And we're just reviewing. Sometimes there's some import errors. Haven't had really a chance to work out some of the finer issues, but typically it works okay. Something went wrong with this one, so I'm just going to delete that. The other one looks good. Something went wrong there. So at least we still have 3 force curves from the bright and the dark area. All right, so now I want to process these. I'm going to fit to the approach curve. I'm going to use a paraboloid Hertz model for the tip. Poisson ratio, typically for polymers, somewhere around 0.4 to 0.5. So I'm just going to choose 0.45. Doesn't change the final modulus too much, that variation from 0.4 to 0.5. Spring constant, which we learned earlier, is 29.21 from the thermal tune. Add that in and finish. Yeah. So now we have our analysis, both in Young's modulus. That seems a little low for something like HDP. I think it should be in the hundreds of megapascal kind of range. So probably some finer tuning of those fitting parameters is needed. Maybe the tip area is wrong, things like that. That's where some sort of like constant known material can help you with determining your tip size. But something which does show a contrast, let's see, how's our adhesion force? So you can see there is a pretty significant difference pretty consistently between the dark and the bright. The bright part of the phase image, and we had like this. Well, I'll go back to imaging mode so you can compare them side by side. So this is our topography image. This is our phase image. So there was something interfering with the phase image here, making it quite different. So whatever it is about this spot here, this dark area, it has a lower adhesive force, which is pretty much just this value here. You can see the force on this y-axis is nanonewtons, and then between this baseline, here we are approaching the sample, and this is us touching the sample, approaching to some force, and then withdrawing. And as we pull away, this is the tip actually bending towards the sample before it gets released and snaps off. So this is considered an adhesive force. So it looks like the adhesive force in the bright or the most common areas of the image is much higher than this dark bit here. Doesn't like there's much of a difference in modulus, but again, I'm suspicious of this modulus analysis. Okay, that covers our quick introduction to some imaging, some phase imaging, and also some mechanical analysis in the Nanosurf Drive AFM. So some of that final analysis stuff will change once some more analysis tools are added into the analysis part of the Nanosurf Studio software. But for now, this is the way you can analyze your results. Or if you're a MATLAB whiz, you can import all that straight into something like that and fit your own models, and that might work a little bit more automatically too. Thanks for watching.